Now let's take the next step and increase the number of inputs as well. You can see we have two inputs, x1 and we have x2, and one output y of t connected via two neurons. Let's call it neuron number 1, neuron number 2. You can see we have now 4 weights because the number of inputs are increased. So each neuron is connected with both inputs. So if we talk about this neuron, you can see it is connected with x1 and also with x2. So with x1 it is connected using a weight w11. Similarly, it is connected with the input number 2, x2, using weight w12. And similarly for second neuron. Regardless of how complex it appears, the process is same. First step is to do the linear combination. So how do we do linear combination for the first neuron? Let's say n is equal to 1. So we will do the linear combination z1 is equal to, we can see w11 x1 w11 times x1 plus, now we can see w12 and x2. So w12 times x2, and recall that we have to add a bias. So even if these inputs approaches 0, the result of z1 will not be 0. Now the second step, it is about the activation. So how do we do activation? Really simple. h1 is equal to activation of z1. In case of sigmoid, it will be written as 1 plus e power minus z1. Very simple. Now for the second neuron, same procedure, z2 is equal to, so for this neuron we have w21 into x1, so w21 times x1 plus w22 times x2. We can see here this and this coming right over here. Okay, and sorry, this should be b1 just for coding, which you might be doing later on. So this is w22 times x2 plus bias b2. So what is our estimated function using two neurons for two inputs? It's really simple. v1, we can see here, this is v1, and at this point we have h1. At this point we have h2 because we have performed these linear combinations and activations. So v1 times h1, v2 times h2, or we can write it in vector form like this. So nothing changes, it's just the number of increased inputs, and it increases the number of weights, but the process is same. First step is to do linear combination, and after that we have to do the activation. What's important here is that each neuron now sees a different linear projection of the input space. By combining these nonlinear projections, the network can model much more complex relationships between inputs and output.